A visitor from beyond our solar system crossed the darkness, swept past the sun, and carried a secret older than almost everything humanity has ever touched. It was not a spacecraft, not an alien probe, and not a mysterious weapon hidden inside a cloud of dust. It was something real, natural, and in many ways even more extraordinary. A comet born around another star, thrown into interstellar space and sent wandering through the galaxy for ages before chance brought it into our neighborhood. Scientists named it 3I Atlas, the third confirmed object from another star system ever detected. When the James Webb Space Telescope examined the gases escaping from it, the results revealed chemistry unlike that of familiar comets, and opened a rare window into the frozen material from which distant planetary systems are built. To understand why this mattered, imagine the solar system as an enormous gravitational island. The sun sits at its center, holding planets, moons, asteroids, and comets in repeating paths. Interstellar objects are different. They arrive too quickly to be captured, travel along open paths rather than closed loops, and eventually escape forever. Until recently, astronomers had never knowingly seen one. Then, within less than a decade, 3 appeared, each offering a brief and precious chance to study material formed under another sun. The first was discovered in 2017 and named 1I's Oumuamua. Its speed and trajectory proved that it came from interstellar space, but almost everything else about it invited questions. It appeared small, faint, unusually shaped, and almost completely inactive. Astronomers realized what it was only after it had already passed closest to the sun and begun racing away. Its strange brightness changes, tumbling motion, and subtle acceleration inspired intense scientific debate and even sensational speculation. Humanity had recognized its first known visitor from another star only when that visitor was already leaving. 2 years later, 2I Borisov provided a clearer picture. Unlike Oumuamua, Borisov behaved like an unmistakable comet. Sunlight warmed its frozen surface, releasing gas and dust that formed a glowing coma and visible tail. Astronomers detected familiar molecules and compared its composition with comets born in our solar system. Borisov was discovered only months before its closest approach, and it moved quickly through the region where detailed observations were possible. Afterward, scientists hoped the next interstellar visitor would be found earlier, shine more brightly, and remain active long enough for the most powerful observatories on Earth and in space to prepare. That opportunity finally arrived in 2025. On July 1st, the Asteroid Terrestrial Impact Last Alert System detected a faint moving object in images taken from Rio Hurtado, Chile. ATLAS normally searches the sky for asteroids that could threaten Earth. Its telescopes repeatedly photograph enormous regions, comparing new images with earlier ones to find points of light that have changed position. Follow-up observations revealed a dramatically hyperbolic trajectory, meaning its orbit was far too open for the sun to hold it. It had entered from interstellar space, would curve around the sun, and then depart along a path that never returned. The designation 3I identified it as the third confirmed interstellar object. ATLAS honored the survey that found it. There was no danger to Earth. The comet remained far away, and astronomers could calculate its motion with increasing precision as more measurements arrived. 3I Atlas was discovered while still hundreds of millions of kilometers from the sun, giving observatories valuable time to coordinate. It was already active at a great distance, surrounded by material released from its nucleus. An inactive rock keeps most of its composition locked beneath its surface. An active comet lifts its frozen ingredients into space, where telescopes can separate their chemical fingerprints from the light. It was a sample of another planetary system delivered directly into view. Its motion also hinted at an ancient history. Scientists can compare an interstellar object's velocity with the movement of stars through the Milky Way and use models to estimate the type of stellar population from which it may have escaped. Those estimates do not provide a precise birthday, and they should not be treated as certainty. However, several analyses suggested that 3I Atlas could be extremely old, potentially older, than our 4.6 billion-year-old solar system. It may have formed around a star born long before the sun, perhaps in a colder and chemically different region of the galaxy. At some point, gravitational encounters could have expelled it from its original system. From there, it may have drifted between stars for billions of years, exposed to cosmic radiation and profound cold. That possibility transforms the comet from a distant speck into a time capsule. Every grain of dust and pocket of ice was assembled from material surrounding another young star. While planets grew, collided, and settled into orbits there, this small body preserved some of the system's earliest ingredients. It crossed distances so large that ordinary human language begins to fail, moving through darkness without a home star and without anyone to observe it. Finally, its path intersected ours during the narrow period in history when humans possessed infrared space telescopes capable of reading its chemistry. The encounter lasted only months, but those months connected laboratories on Earth with processes that occurred around a distant star billions of years ago. As 3I Atlas approached the Sun, its surface warmed and its ices began turning directly into gas. This process, called sublimation, dragged dust away from the nucleus and created a brightening coma. Water requires more warmth, while carbon dioxide and carbon monoxide can drive activity much farther from the Sun. By measuring how the comet changed with distance, astronomers could investigate which substances controlled its behavior. Because the comet traveled quickly, every observation mattered. Missed time could not be recovered, and once the visitor moved outward, its gases would weaken until even the largest telescopes struggled to detect them. The James Webb Space Telescope was uniquely suited to the task. Webb observes infrared light, which contains signatures produced when molecules absorb or emit energy at specific wavelengths. By spreading the comet's light into a spectrum, scientists could identify substances invisible to ordinary cameras. Tracking the object was challenging because Webb was designed mainly to study targets at immense distances that appear almost fixed against the sky. Engineers nevertheless guided the telescope with extraordinary precision, allowing its instruments to follow 3I Atlas and examine the coma both before and after the comet passed the Sun. Instead of producing a simple photograph, Webb gathered a chemical inventory written in bands of infrared light. The first major result was the comet's remarkable abundance of carbon dioxide. Early Webb observations showed a coma dominated by carbon dioxide relative to water, an extreme balance compared with typical comets from our solar system. Rather, the proportions suggested that 3I Atlas formed, evolved, or was processed under conditions different from those experienced by most local comets. Carbon monoxide was also present, and later observations revealed changing proportions as the comet moved away from the Sun. These gases are powerful clues because their survival depends on temperature, radiation, and the location where ice is formed. The comet's mixture pointed toward an environment colder, more distant, or chemically distinct from the region that produced many familiar solar system bodies. Then Webb detected methane. This was the first direct detection of methane escaping from a confirmed interstellar comet, and the result became even more valuable when scientists measured its isotopic composition. The ratio of deuterium to ordinary hydrogen can preserve information about the temperature and chemical environment in which a molecule formed. Methane in 3I Atlas carried an unusually high deuterium signature. Water also showed a distinctive isotopic pattern. Together, these measurements indicated that the comet's ices were assembled under very cold conditions, unlike those that shaped known comets in our solar system. In extremely cold environments, chemical reactions can concentrate deuterium in water and organic molecules. The levels measured in 3I Atlas suggested formation far from its parent star, perhaps after some ingredients had already been processed inside a frigid interstellar cloud. In other words, the comet may preserve material from two stages of cosmic history: the molecular cloud that existed before its star was born and the young planetary disk that later surrounded that star. It was a frozen record of the cloud, disk, and temperatures that helped create that system. Methane also raised questions about how deeply radiation had altered the comet. During a journey lasting millions or billions of years, energetic particles would bombard its exterior, changing molecules and building a processed crust. Yet heating near the Sun can strip away surface layers and expose material protected beneath them. Scientists therefore considered whether the gases observed by Webb originated from ancient, relatively unaltered ice below the radiation-damaged exterior. Some molecules entering the coma may have been sealed in darkness since the comet's formation. They remained hidden through the birth and death of civilizations on Earth, then escaped only because this wanderer happened to pass close enough to our Sun for its surface to erode. Scientists detected water, carbon monoxide, carbon dioxide, methane, and methanol, while mapping how gases were distributed around the nucleus. Some substances appeared in asymmetric structures, suggesting jets, uneven heating, or different volatile reservoirs inside the comet. Dust measurements indicated a strong contribution from amorphous silicates, grains whose atoms lack the orderly structure found in crystals. That mineral pattern appears different from the more crystalline mixtures common in many solar system comets. Each difference must be interpreted carefully, because comets evolve and observations sample only escaping material. Even so, the combined evidence showed that 3I Atlas was chemically and physically unlike any object previously examined at comparable detail. Astronomers detected neutral nickel and iron atoms in the coma, with nickel appearing unusually strong during parts of the comet's passage. Metals have been observed in comets before, but releasing them at low temperatures requires an explanation because solid metal grains should not simply vaporize so far from the Sun. One possibility involves volatile metal-bearing compounds, such as carbonyls, that can escape and then break apart under sunlight, releasing individual atoms. Researchers are testing models of subsurface heating, changing ice structure, and chemical carriers. Instead, it offers another clue about how exotic compounds can store and transport metals inside cold cometary material. The Hubble Space Telescope captured high-resolution images, helping astronomers study the nucleus hidden inside the luminous coma and constrain its size. Measuring a cometary nucleus from far away is difficult because the surrounding dust can overwhelm the solid body's faint signal. Early estimates therefore covered a broad range and improved as models and observations accumulated. Other spacecraft watched from different locations, including missions near Mars and Jupiter. ESA's JWST spacecraft observed the comet shortly after perihelion, while X-ray observatories examined interactions between the coma and the solar wind. Every instrument viewed a different layer of the same event, turning one brief passage into a multidimensional scientific record. SphereX, a space observatory designed to map the sky in infrared wavelengths, followed the comet's changing activity after its solar encounter. Ground-based optical and radio telescopes measured additional gases, dust, and motion. Arrays, such as ALMA, searched for molecules that reveal organic chemistry and the conditions inside the coma. Mars orbiting spacecraft improved the predicted trajectory by observing the comet from a location far from Earth, demonstrating how planetary missions can contribute to studies they were never originally built to perform. Researchers across countries shared measurements rapidly because delay would reduce their chances. The visitor would not pause while proposals were reviewed or schedules were debated. The cooperation was remarkable because no single telescope could answer every question. X-rays showed how solar wind particles interacted with the coma. Precise astrometry refined the orbit. Together, these methods built confidence that 3I Atlas was exactly what its behavior suggested, an active natural comet from interstellar space. Its unusual features were scientifically valuable, but they did not require an artificial explanation. Nature routinely produces outcomes that look unfamiliar when humanity observes a category containing only 3 known examples. With such a tiny sample, unusual often means new to us, not impossible without technology. That distinction became important as claims spread online that the object might be a spacecraft or alien probe. Curiosity about extraterrestrial intelligence is legitimate, and scientists can test specific predictions when instruments allow. Radio searches looked for artificial transmissions associated with 3I Atlas and found none. Its acceleration followed the combined effects expected from gravity and cometary outgassing. Its coma, tail, molecules, dust, and response to solar heating matched natural comet physics. No observation demonstrated engines, controlled maneuvers, manufactured structures, or technological signals. The evidence supported a far more grounded conclusion. 3I Atlas was a genuine fragment of another planetary system, and its natural origin made it no less astonishing. The verified story was already larger than the rumor. What makes this visitor important is that astronomers usually study other planetary systems from many light years away. They analyze starlight filtered through exoplanet atmospheres, or examine disks around young stars as unresolved bands in glowing clouds. 3I Atlas brought actual material from such a system into our solar neighborhood. No spacecraft needed to cross interstellar space. Gravity and chance delivered the sample, while sunlight released it into a form telescopes could read. Scientists could compare its carbon chemistry, water, methane, isotopes, metals, and minerals with local comets. Every similarity suggested shared physical processes across the galaxy. Every difference revealed the range of environments in which stars, planets, and small icy bodies can form. The comet also changed expectations about how common interstellar wanderers may be. Before Oumuamua, their population was theoretical. After 3 detections in less than 10 years, it became harder to imagine that interstellar space is empty. Planet formation is violent. Young worlds scatter smaller bodies. Giant planets disturb orbits. Binary stars exchange material, and passing stars can eject comets entirely. Across billions of systems, those processes should produce an enormous invisible population of wandering debris. Most objects would be too small, dark, or distant to detect. The 3 known visitors may represent only the bright edge of a vast stream continually crossing the solar system. Better surveys will reveal whether that inference is correct. New observatories are designed to search the sky more deeply and repeatedly, increasing the chances of finding future visitors earlier. Early detection is critical. A comet discovered before it approaches the sun gives astronomers time to measure its inactive state, watch its first eruptions, schedule Webb and Hubble, and coordinate observations from spacecraft across the solar system. One day, enough warning might even allow a probe to intercept an interstellar object. Such a mission could photograph the nucleus at close range, analyze dust directly, and measure material with instruments far more sensitive than remote telescopes. 3I Atlas showed what careful preparation can achieve. It also revealed how much more could be learned if the next target were discovered sooner. There is something humbling about the timing. The comet may have wandered for longer than Earth has existed. During almost all of that journey, humanity was absent. Even after our species appeared, we lacked the tools to recognize an interstellar orbit or identify methane across millions of kilometers. Had 3I Atlas arrived a few centuries earlier, it might have appeared as nothing more than a faint comet, briefly recorded, and then forgotten. Instead, it arrived after the construction of Webb, Hubble, SphereX, advanced radio arrays, automated surveys, and spacecraft spread across the solar system. For one fleeting passage, the right visitor met the right civilization with the right instruments. Now 3I Atlas is leaving. The sun's gravity bent its path but could not keep it. Its activity is fading as distance restores the cold, and eventually it will become too faint for meaningful observation. It will continue into interstellar darkness, carrying most of its nucleus untouched. Humanity may never know which star formed it, which planets once shared its system, or what encounter sent it away. Yet for a brief moment, the comet opened itself through gas, dust, and light. It allowed scientists to measure matter created under another star and preserved across cosmic time. That is the real wonder of 3I Atlas. Not that it was artificial, but that nature sent us an ancient message, and for once we were ready to read it.